You've probably heard that mathematics is the language of the universe. And if that's true, well, the most fundamental words, the things we use to build everything from our economy to our understanding of the cosmos, are numbers. So in this explainer, we're going to decode that language together, starting right at the very beginning, with the idea of the number itself.
But first, just take a second and try to imagine a world with no numbers, seriously. How would you trade anything? How could you possibly build a house with any precision? How would you even know what time it is? I mean, it's pretty much impossible to picture, right? That's because numbers are woven into the very fabric of our lives. They are the absolute bedrock of how we build, communicate, and organize our entire civilization.
So here's our game plan. We're going to go on a little journey. We'll start back in a time before numbers to see why we even needed to invent them in the first place. Then we'll build our modern numbers system piece by piece. After that, we'll learn the universal grammar of math, uncover some really cool shortcuts, kind of like math hacks, and finally, we'll see how it all clicks together in the super powerful world of algebra.
All right, let's dive right in. We're hitting rewind on history, going all the way back to a time before numbers even existed. Why? Because we need to understand the basic human problem that led to one of our single greatest inventions, the idea of counting.
So, our story kicks off about 100 centuries ago. You've got farmers in the Middle East who need to keep track of their stuff, right? So they start using little tokens, 1 stone for 1 sheep. Simple, but totally revolutionary. Then fast forward a few thousand years to ancient Egypt. They need to divide land and food and bam, fractions are born. But there's still a huge idea missing. How do you represent, well, nothing? It wasn't until the 5th century in India that the concept of zero finally joins the party. And just a couple of centuries later, those same brilliant minds in India gave us negative numbers to handle things like debt. And here's the key takeaway. Each of these inventions wasn't just some abstract idea. It was a clever solution to a very real problem.
Okay, so we know why we needed numbers. Now let's actually build the system we use every single day, one layer at a time. The absolute best way to picture this is to think of those Russian nesting dolls, where each new doll fits right over the last one. Every set of numbers we add is just like a new doll, adding a whole new capability.
We're going to start with the smallest doll, the most basic set of all, the natural numbers. These are your classic counting numbers, 1, 2, 3, 4, and on, forever. They're literally the first numbers all of us learn as kids when we're counting on our fingers. But see, there's a little problem with just the natural numbers. They're fantastic for counting all the stuff you have. But what about when you don't have anything? What happens when the basket is empty? How do you write that down?
And the solution? Well, it was so simple it was revolutionary. We just add one more powerful idea, the number 0. And with that one single digit, our number system can now show not just what is there, but also what isn't. This gives us our next nesting doll, the whole numbers.
Okay, cool. So we can count things, and we can represent nothing. But what about the opposite of having something? How do we talk about owing someone money, or a temperature that drops below freezing? Our whole numbers can't do that.
So, we open up our nesting doll again, and inside we find the next layer, the integers. This set includes all of our whole numbers, plus their perfect mirror images, the negative numbers. Now our number line isn't just a ray starting at 0, it's a full line stretching out to infinity in both directions, positive and negative.
So far, we've only talked about whole units. But what about all the spaces between the numbers? For that, we open the doll one more time to find the rational numbers. This is basically any number you can write as a simple fraction. The thing about rational numbers is that they're pretty predictable. When you write them as a decimal, they either just stop dead, like 0.5, or they get into a nice, neat repeating pattern, like 0.333 repeating forever. And now we get to the really weird ones. The ancient Greeks stumbled upon numbers that just didn't play by the rules. You couldn't write them as a nice, simple fraction. And their decimals, they go on forever without ever repeating. Just total, unpredictable chaos. These are the irrational numbers, like the famous pi or the square root of 2, and they fill in every last remaining gap on our number line.
And what's so cool is how this all fits together. You've got the naturals inside the holes, which are inside the integers, which are all part of the rationals. That's our last nesting doll. And then, sitting right alongside that big doll, you have the irrationals. You put those two huge groups together, the rationals and the irrationals, and you get the whole shebang, the real numbers, every single possible point on the number line.
So we've got our words, our numbers. Now it's time to learn the grammar. We need a set of rules that make sure a math sentence means the exact same thing to me,
to you, and to anyone, anywhere in the world.
And that universal grammar is called the order of operations. You probably remember it as PEMDAS. Now, this isn't just some random list of rules somebody made up. Think of it like a protocol, a shared agreement that guarantees we all read the math the same way and get the same answer. You always start with parentheses, then you deal with exponents, then you do all the multiplication and division as you see them from left to right, and finally, you do all the addition and subtraction, also from left to right.
Okay, let's actually put this to the test. Look at this expression. The very first rule in PEMDAS is P for parentheses. That means we have to deal with what's inside the grouping symbols before anything else. So 3 times 2, that's 6, and 6 plus 2, that's 8. Okay, the expression is simpler now, but we're not done.
Next up is E for exponents, so that 6 squared becomes 36. Now this is really important. PEMDAS tells us we have to do the multiplication before the subtraction. So 4 times 8 gives us 32. And now finally, all that's left is a simple subtraction. 36 minus 32 leaves us with our one correct universal answer, 4. See how that structure just walks you right to the solution?
Okay, so that shows the rules perfectly. But what about the shortcuts? You know, the secret logic that makes math way more flexible. Let's talk about the properties of real numbers. Honestly, think of these as powerful math hacks that can make solving problems so much easier.
First up, we have the commutative property. And this one's super simple. For adding and multiplying, the order just doesn't matter. It's like putting on your shoes. You can put on the left one and then the right one, or the right one then the left one. Who cares? The end result is exactly the same.
Now this table is basically your cheat sheet of math hacks. The associative property is all about grouping. It means you can rearrange parentheses in a long addition or multiplication problem however you want. It's all about flexibility. The identity properties are our neutral tools. Adding 0 or multiplying by 1 doesn't change a thing. Then you have the inverse properties, which are like a universal undo button. They're how we get back to 0 or 1, and that's the secret to solving equations. And finally, the distributive property. This one's a real powerhouse. It's how we break apart tricky multiplication problems into much simpler pieces. You don't have to memorize all the names, but understanding what these do, that'll make you a way more powerful problem solver.
So, let's recap. We have our numbers, we have our grammar, and we even have our shortcuts. We've built this whole system for working with numbers we know. But what happens when we have an unknown? That's when we take the final, incredible leap from just numbers to algebra. And we do that by introducing one new idea, the variable.
And this is it. This is the start of algebra. An algebraic expression is just a mix of constants. Those are just regular numbers that don't change, and variables, which are letters like x or y, that are basically placeholders for a value we don't know yet. And this is what lets us go from just doing basic calculations to actually building models of the world and solving for unknowns.
And you know what the beautiful thing is? All the rules we just learned, like PEMDAS, they still work perfectly. Think of that x as a little mystery box. We can plug any number we want into that box and then just follow the rules. So if we plug in 0 for x, the expression becomes -7. If we plug in 1, it becomes -5. If we plug in -4, we get -15. See? Algebra isn't some scary new thing. It's the exact same game we've been playing all along, just now we're doing it with a mystery box.
So think about it. From that very first farmer just making a scratch in the dirt, all the way to the complex equations that run our modern world, it all comes from these basic building blocks. We've gone from simple counting to complex calculations